Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at integration by parts so we can answer questions from exercise 11F. So let's begin by creating the integration by parts rule, which is to rearrange the product rule. So taking your product rule, and what we're going to do here is subtract v du by dx from both sides. Now, I generally prefer the product rule in the FG notation, but this is an equally equivalent notation here. Then integrate each term. So, if we're integrating uv and the differential of that with respect to x, then the integral of the differential will just cancel out and we'll get uv underneath this term here. And then these two terms here are going to stay as they are. So it's only the far left-hand term that will cancel out. And this here is now the integration by parts rule. We just generally write it the other way around. It's given to you in the formula booklet just like this term here. So we can see here it's made up, integration by parts, of two components. One component and two components that are being multiplied together. And in order to use the integral by parts rule, on the other side we're going to see that u needs to be differentiated and dv by dx needs to be integrated in two positions. So in this case here, we're not going to differentiate or integrate both of them, we're going to differentiate one of them and integrate the other one. So let's see this in action then. The function you're trying to integrate needs to be written as a function multiplied by an integral. When using the product rule, we start by labelling the functions u and v, but when we're using integration by parts, we have to start by labelling them u and dv by dx. And as I said before, this term here is going to need to be integrated, this term here is going to need to be differentiated, because you can see where things appear on the other side and what you're going to need from the integration by parts rule. So let's have a go at one here. We've got the integral of x times cos x. Now in this case here, we need to choose one part to be u and the other part to be dv by dx. Now it's absolutely fine integrating and differentiating cos x. That would just rotate round kind of onto itself. So this doesn't really help us simplify this problem here. But if we can reduce this x term here, maybe by differentiating, then that will help the integral out a lot. If we were to integrate this term here, then that would not help the integral, it's just make things harder. So in this case here, it's a wise idea to choose u to be x, so that we get du by dx is 1, so let's try that. So a good idea is to set any multiples of x or any powers of x equal to the u part in your integration by parts. So the integral of x cos x, what we're going to do is we're going to set u equal to x, and the differential of that is 1. Then the other component of it is dv by dx, and that's cos x. The integral of that is sine x. So you integrate one part, differentiate one part, integrate the other parts. And let's now apply the integration by parts rules. So on the left hand side is our integral. That's what we're trying to work out. This is going to equal u times by v. So x times sine x minus the integral of v, which is sine x, times by du by dx, which is just 1. So it's just the integral of sine x on the right hand side there. You can see how all of these terms are matching up here, like that. Now, what we've created here is a second integral. So when you do integration by parts, you're actually still going to have to integrate something on the right hand side afterwards. So in this term here, we're now integrating something that's a lot easier because we've reduced the power on the x by 1, so it's now just a term of 1. So the second integral here is going to be the integral of sine. The integral of sine is minus cos, but because we've got a negative at the front here, negatives cancel out. Our final answer here is going to be x sine x plus cos x. Okay, so it does take a while to get used to these. What we're generally going to be doing in these types of questions here is setting the power of x term equal to u, differentiating it down so that it gets easier And then the other term we're going to just be integrating. Apart from when it looks like this. Now, x squared ln x, I'm immediately looking at those and thinking, well, which ones can I differentiate, which ones can I integrate? And so far, we haven't seen how to integrate ln x. So the only thing we can do with ln x is to differentiate it. So we'll have to call u ln x. And we need to differentiate that. We know what the differential of of ln x is. That's 1 over x. And for the other term, x squared, that's going to need to be the dv by dx part. So we need to integrate this part here to a third x cubed. Then we apply the integration by parts rule. So it's going to be u times v minus the integral of u times by du by dx, which is x squared. So du by dx, which is 1 over x with respect to x. And now what we see here is the integral on the right hand side here is a lot more simpler. It's just a power of x integral. Reason being is that ln x differentiated to 1 over x, that's just a power of x. X cubed will obviously integrate to another power of x. So these two here will just simplify to a power of x term. So let's do the integration on the right hand side here. We can obviously see where these are all fitted in. So it's still going to be x cubed ln x over 3, and then it's going to be the integral of x squared over 3. Increase the power by 1, divide by the new power in this term here. And we get x cubed ln x over 3 minus x squared, x cubed over 9 plus c. So in this case here, so choosing u equals ln x has removed it from the integral part and actually helped us simplify it. So in this case here, usually we'd be setting this thing equal to u, because that will help reduce things down. In this case here, we're actually going to set ln x equal to u, because we have no idea how to integrate ln x at the moment. We're going to have to differentiate it, so that means the other term is going to have to be labelled dv by dx. Okay, next term here then, so we've got a power of x times by e to the x. Now in this case here, we're going to be differentiating the x squared term, and well, it wouldn't really matter what we did to the e to the x because it's just going to stay the same anyway, but in this case we're going to be integrating it. And in this case here, it's one of these questions where we're going to have to do integration by parts twice in a row. So let's see how this works. We're first going to be doing u equals x squared, differentiate that and we get 2x. Notice here how when we differentiate, the power on the x's gets smaller each time, which simplifies the next integral that we're going to be doing. dv by dx is e to the x, integrate that to e to the x. So now we have to substitute the integration into our by parts formula. In this case here, the integral we're trying to work out is equal to u times v, so it's x squared times e to the x, minus the integral of v, which is e to the x, times du by dx, which is 2x. And we can see how all of those have been substituted in. And now with integration by parts, you've always got an extra integral you need to work out on the right hand side, but in this case here we have no idea how to integrate this, but it looks like we've still got two parts to it, 2x and e to the x, so we're going to do integration by parts again. So we're now going to be integrating 2x e to the x. Let's set u equal to 2x, and when we differentiate this, the power reduces, which is going to make the third integral that we're going to work out a lot easier. Integrating e to the x back to v, which is e to the x, and using the integration by parts rule again. So it's going to be u times by v, 2x times e to the x, minus the integral of v, which is e to the x, times by du by dx, which is just 2. Now in this case here we can see how all of these have been substituted in, and the integral of 2e to the x is much more straightforward to do. We can just do that straight away. That's going to be 2e to the x again. Now what's going to happen here is our final answer to this question here is going to be x squared e to the x minus all of this. So in this case here, let's just simplify what we've got here. So in this case here, the final answer to this question here is going to be x squared e to the x minus 2x e to the x. Double negative will make it plus 2e to the x and plus c. It doesn't really matter whether plus c is a minus c or not, it's just a constant at the end, so it doesn't really need a sign change at all. So there we are, that's how you do integration by parts twice. Now oh wait, we've got one more to go, and we're going to see now how we integrate ln x, and it's a little bit of a trick here, and it's in the integration by parts chapter for a reason. And you're probably thinking here, well, we haven't got two parts, we've got a ln x and nothing else. We've got no other second part to this function here. Now, what we're actually going to do here is we're going to be a bit cheeky. We're going to differentiate ln x using the by parts rule, and we're going to use dv by dx as equal to 1. Okay, so we're treating this integral here as 1 times ln x. So in this question here, we know how to differentiate ln x, so let's use that to our advantage. We're going to be differentiating that to 1 over x. And then dv by dx is equal to 1, so we're going to be integrating that back up to x. And you can see what's going to happen here when we use the du, dx, and the v part. Those two bits are going to cancel out there. So in this case here, now what you can do is you can replace in this relationship in the for the integration by parts. So it's going to be the integral we're working out, ln x times 1 equals u times v, that's x times ln x, minus the integral of v du by dx, so that's x times 1 over x. And we can see here that the integral on the right hand side now is going to be very simple. It's just going to be the integral of 1, and in this case here that's just going to be x. So the final answer here is x ln x minus x plus c. So there we are, that's the answer to that question there then. That is how you integrate ln x. But obviously we still have these limits to go, so let's go ahead now and substitute these limits in. And remember, when we're substituting in limits, we don't need the plus c part. So substituting in 2 and substituting in 1, do 1, take away the other. Remember, ln 1 is just equal to 0, so it's 2 ln 2 minus 2, add 1 for the double negative there, and we get 2 ln 2 minus 1. And that's our final answer there. So that's how you integrate ln. It's a special case where you treat it as an integral by parts. Ln x is the u part, dv by dx we set equal to 1. So we treat it as a special type of integral where it's 1 times ln x. So, a general summary of how do you choose which part of your integration by parts is going to be set equal to u. And it generally goes in this order here. First things first, we're going to be setting u equal to any ln things, like ln x, or maybe you might have something like ln 2x in your integral. The next thing you would set u equal to, if there are no logs or no lns in your integral by parts, is any algebra. So for example x, x squared, x cubed, etc, etc. And you won't get onto this unless you're doing further maths, but the next things you would probably set u equal to is any trigonometry or exponentials. But it's basically one of these two functions here that you're going to be setting u equal to, logs taking priority over algebra. So 3 questions for you to have a go at then. Pause the video and try this first question out. Right, okay, so first thing that hopefully you did with this first integral here is to do ln x times by x to the power of minus 3. So treating the fraction as a multiplication of a negative indice. And then we're going to set the appropriate functions equal to u, and this one's u, and this one's dv by dx. So in the integration by parts rule, we need to take ln x and differentiate it. So du by dx is 1 over x, and we need to take dv by dx equal to x to the minus 3 and integrate it to get back to v. So it's increase the power by 1 divided by the new power. increasing the power by 1 will make it minus 2, and then multiplying that power, or dividing by that power, will make it minus a half. Okay, so this is the method we're going to use here. So the answer now is going to be uv minus the integral of v du by dx from the formula booklet. And let's now apply this. So it's going to be minus 1 over 2x squared, I'm just simplifying this bit here, times by ln x. Then it's going to be subtract v, which is minus a half x to the power of minus 2. I'm going to bring the minus out to the front and make that a double negative at the front there. And I'll bring the half out to the front, I think, as well. So it's just going to be x to the power of minus 2, multiplied by du by dx, which is another x to the minus 1. So let's move up to the top here. Our answer is going to be minus 1 over 2x squared ln x. And now I actually have to integrate the thing on the right hand side. So when you're integrating by parts, you don't actually get rid of the integral that you have to work out. You just help it along a little bit and you help simplify it. Now, x to the power of minus 2 times x to the power of minus 1 is x to the power of minus 3, simplifying this bit here. So then let's have a look at integrating this. In this case, we increase the power by 1, divide by the new power. Increasing minus 3 will go to minus 2, and timesing the front by that new power, plus c. So our final answer here is going to be 1 over 2x squared. And in fact, let's leave it all expanded for the moment, so we might simplify afterwards. Then it's going to be minus a quarter x to the minus 2, which will be x squared on the bottom of a fraction. So in this case here, we could factorize out the 1 over 4x squared and put a 2 ln x minus 1, or plus 1, because we factored out the minus there. That would probably be a simplified answer there. Oh, plus c. Okay, so there we go. Hopefully you got something similar to that. Have a go at the second one then, and you might need to use these integral rules on the right hand side here. So pause the video and try this question out. Okay, I suppose the one that wasn't on this list was the differential of sec x is sec tan x, so hopefully you did spot that. So in this case here, we're going to set u equal to x, and dv by dx equal to sec x tan x. Now, what on earth does sec x tan x integrate to? Well, if you remember from your differentiation part of your formula booklet, that is equal to sec x. And we're going to differentiate the x part, the nice easy bit. That's just going to now be a 1. So applying integration by parts here, it's u times v, x times sec x, minus the integral of v times du by dx. That's the integral of sec x. And the bit of the formula booklet you're now going to need is coming up here. We need to integrate sec x, and we can see on the bottom row there, it's going to be ln bracket sec x plus tan x. And remember, we need these modular symbols around it because that's how you integrate tan. So you integrate using the ln function. So it's plus c. There we are. That's the final answer to that question there. Okay, and one more to go then. Have a go at integrating this one here. It's got an x squared part. That's ringing bells to me, thinking, well, I'm probably going to have to integrate by parts twice with this one here. Pause the video and try this question out. Okay, so the first thing I'm going to do is I'm going to think about how the structure of my answer is going to look here, and I'm going to need lots of space for this one, so let's give myself 3 columns for it. So in this case here, u is going to equal x squared, du by dx is equal to 2x, and dv by dx is equal to sine 4x, and I need to integrate this one here, So integrating this one, sine will go back round to minus cos. So v is equal to minus a quarter cos 4x. And now let's apply integration by parts. The answer is going to be minus 1 over 4 x squared cos 4x minus, but I'll make it plus for the negative that's on here, the integral of 2x over 4, so that's going to be x over 2 cos to the 4x dx. Now, we're going to have to use integration by parts here again on x over 2 cos to the 4x. So in this case, u is equal to x over 2. Differential of that is a half. And the dv by dx part is equal to cos 4x. And that will integrate to 1 over 4 sine x. Remember that it's really important you understand that one part's differentiated, one part is being integrated. So now applying by parts, just for this part of the integral here, it's going to be u times v, so that's going to be x over 8 sine 4x. And then for the last part, it's going to be minus the integral of v times du by dx, that's going to be minus 1/8 that I'll pull out to the front, and then it's going to be sine 4x dx. And the integral of this right hand side here is going to be integral of sine goes back to minus cos, so it's going to be a plus here, divided by 4, so that's 8 times 4 is 32, so it's going to be 132 cos 4x plus c. So what's the final answer to this question here then? The final answer to this question is going to be minus 1/4 x squared cos 4x plus x over 8, plus we're now integrating, we're now adding on the integral of this thing here, which is this thing down here, x to the 8 sine 4x plus 1 over 32 cos 4x plus c. There we are, that's how we integrate that thing there, so voila. Oh wait, I don't, there we are, voila. Here is the integral for this question here. Quite a long one there. Generally, when you've got an x squared in your integral, you are going to be having to do integration by parts twice. And if you have an x cubed in there, good luck, you're going to have to be doing that 3 times. Although there might be probably a trick. I've only ever seen exam boards give integration by parts twice, where you've got an x squared term here. I've never seen it where you've had to do it 3 times. Kind of just be a bit boring then, won't it? Okay, so there we are. A very powerful tool. It's not always used though. Do try and have a look at whether you can simplify the algebra first before you have a go at integration by parts. Integration by parts would effectively be my last chance strategy to see if I can work out how to integrate a question. I would always look to try and simplify the algebra first, or combine the algebra in some sense, before I have a go at integration by parts. But there's lots of practice on page 306, questions 11F. Persevere through the difficult ones, challenge yourself on the exam style questions, the problem solving style questions, and ask your teacher for help if you need any. Thanks very much for watching.